Caves covered by vegetation, fauna and soil can record information about the surface ecosystem above them. This makes them a valuable resource for scientists seeking insights into terrestrial systems. Among the numerous caves in Switzerland, Mélandré Cave stands out as a geotope of national importance. The extensive scientific research conducted in the cave today is indebted to the tireless efforts of those who have explored its caverns in the past.
I'm interested in caves mainly because it's one of the last unknown territory on our planet Earth. And my interest focuses on discovering these passages, exploring some unknown ways through the cave to understand how these cave passages form and what they host in terms of sedimentary archive, and eventually to extract some scientific information out of this to reconstruct the outside environment.
Did you know caves offer a unique opportunity to study ecosystem changes by analysing the carbon isotopes preserved in speleothems? These mineral deposits can provide a record of carbon movement from the surface to the underground environment. However, to accurately interpret this record, it is necessary to have a thorough understanding of the carbon cycle.
This case study will be about using stalagmites to detect the radiocarbon bomb spike, and from that to learn something about the age spectrum of soil organic matter above the cave.
The Mélandré Cave is a prime example of a site where this type of research is being conducted. It is home to one of the most extensive carbon monitoring programs, providing crucial insight into contemporary ecosystem processes.
Mélandré is a large underground river which has attracted a lot of scientific interest over the last 40 years, especially to understand how the water circulates in a cave system. And on top of that, it has attracted quite a lot of interest for biospeleological studies, paleoclimatological studies, or just understanding the cave dynamics and the processes driving the cave environment.
So carbon in caves is primarily coming from the surface, from the soil, and also from the dissolution of the carbonate bedrock. So in that we have a tool that can help us to really learn something about the surface ecosystem.
Stalagmites in caves can help us to study changes in the soil carbon cycle over time. However, understanding the cave carbon cycle is a complex task because the carbon entering the cave has different sources. Stable carbon and also radiocarbon isotopes can be used to distinguish these sources, but they both undergo chemical changes during their journey from soil to cave. This is where the bomb spike comes into play. The bomb spike is a distinctive anthropogenic signature that originated from nuclear weapons testing in the 1950s and 1960s. The term refers to a significant increase in the atmospheric concentration of radiocarbon as a direct result of these nuclear tests. It serves as a tool for tracking both carbon distribution among global carbon reservoirs, such as soils and speleothems, and also carbon persistence. Let's have a closer look at how this works. Speleothems that have captured the bomb spike signature can be used to unravel the age distribution of soil organic matter. By comparing the radiocarbon signal with the speleothem and contrasting it with the original atmospheric signature, we can reconstruct the soil age distribution. Note that different cave systems show different bomb spike signatures depending on factors like climate and soil composition. Warm, semi-arid caves with thin soil and sparse vegetation are more likely to have a strong bomb spike signal, while caves with thick, waterlogged peaty soils have the tendency to show a weaker signal. In fact, not all speleothems exhibit the bomb imprint.
So for one, the stalagmite has to have grown over the last 100 years and at sufficiently high growth rate that we can resolve the bomb spike with our current techniques. So that also depends a little bit, of course, on the method that we use, and we can, for example, drill little bits of powder out, or we can use now also laser ablation, which then can allow us to get to much higher resolution and find the bomb spike in stalagmites that are have grown much slower. And the other concern, of course, is the hydrogeology. So if the signal takes too long to travel from the surface to the cave and becomes too diluted with other water masses or influences on the way, then it also becomes very difficult to detect this signature in the stalagmite.
The bomb peak found in stalagmites presents a valuable opportunity to study the carbon cycle and ecosystem processes in a specific location. The isotopic signature analysis helps us to estimate carbon age and origin in the soil, providing insights into carbon storage, release rates, and environmental impact. Therefore, the bomb peak is a powerful tool for studying the carbon cycle and linkages between surface and subsurface ecosystems.